Hi, in this video, I'll be solving this problem from the China Gross Math Olympiad of 2010. The China Gross Math Olympiad, or CGMO, is a math competition for girls that was started in 2001 with the goal of encouraging more high school girls to engage in advanced, creative, Olympiad-style math. Originally, it was designed for China, so teams from different regions of China would compete together. But after a few years, the organizers started inviting teams from other countries as well. And the United States has been sending teams to the CGMO since 2007. Our team members are selected based on results of the USA Math Olympiad, USAMO. The very first year we went, team member Sherry Gong tied for first overall. Now I want to spend a few minutes talking about Sherry Gong because she's very special. Because also in 2007, she won the gold medal at the IMO. If you look up Sherry Gong on the IMO website, you find out that she went to the IMO 5 times. The first 3 representing Puerto Rico, where she grew up. Well, that's not counting 2006. She didn't go in 2006. That was the year she went to the International Physics Olympiad and won a silver medal there. So if you count back 6 years from 2007, then you'll see that she actually started going to the IMO while in middle school and actually winning a medal while in middle school. Now in 2010, the year that this question came from, the US sent 2 teams of 4 students each. One of the 2 teams placed second overall. Of the 8 contestants, 5 won gold, 1 silver, 1 bronze, and 1 honorable mention. And guess what? Sherry Gong was one of the coaches. At the time, she was an undergraduate student. She went on to get her math degree at Harvard, her PhD at MIT, did her postdoc at Stanford, and is now teaching at Texas A&M. Anyway, so let's dive into this problem. The CGMO takes place over 2 days. Each day's got 4 hours and 4 problems. So on average, they expect each problem to take about an hour. This problem is number 3 on day 1. Prove that for every given positive integer n, there exists a prime p and an integer m such that A, p is congruent to 5 modulo 6, B, p is not a factor of n, and C, n is congruent to m cubed modulo p. Given a positive integer n, we're either looking for or proof that there exists a prime p and an integer m such that, and the main relation that we're looking for is part C. That's the relation we're looking for. And these are the requirements for P. P is limited by those 2 conditions. All right, let's strategize. In the previous video, I talked about how you really need to know modular arithmetic if you want to do competition math. And so if I look at this and I see a power and a prime modulo, then that triggers this fact about modular math that you should know. And in competitions, you don't have to prove it. You can just say it and they accept that you know it. And it's this: if P is prime, and if n is not a multiple of P is not a factor of n, then n to the power P minus 1 is congruent to 1 mod P. I'm pretty sure this is the property they're looking for because the condition that n is not a multiple of P is also part of the problem. So here's my power, here's a power, and this property says 1, but the question asks for n. So I'm just going to get n out of this by multiplying both sides by n. If I multiply both sides by n, then on the left I have n to the p, and on the right I have n. My first thought is, what if I make this equals to m cubed? then I'm done, right? Because then m cubed is congruent to n. If I set m is equal to n to some power k, then on the left side, I have n to the 3k, and on the right side, I have p. So that tells me that p is equal to 3k. And then I realized it doesn't quite work because 3k is a multiple of 3. So it's going to be congruent to either 0 or 3 mod 6. That doesn't work because the question wants p is congruent to 5 mod 6. So oops, doesn't work. I need to find another power of n that's also congruent to n. How do I get another power of n and still stay at n? Well, I use this property, the congruence above that, because it's congruent to 1, multiplying by it doesn't change n. So I'm going to take these two congruences and then multiply them side by side. If I multiply them side by side, then on the left, I get n to the 2p minus 1. And on the right, I still get n. Let's try it. What if I set this equal to m cubed? And again, m is n to some power k. Then I have n to the 3k is equal to n to the 2p minus 1. 3k is equal to 2p minus 1. I solve for p, I get 2p is equal to 3k plus 1. At this point, I don't want to just divide by 2 because that'll get me a bunch of fractions. I don't like fractions in modular arithmetic. I know how to fix this because if you're familiar with modular arithmetic, then you see the solution right away. Because 1 and 4 are the same in modular 3. 2p is congruent to 1 mod 3. In modular 3, 1 and 4 are the same because 4 has a remainder of 1. That means p is congruent to 2 mod 3. This is good because 2 mod 3 is consistent with 5 mod 6. The condition in the problem says p has to be congruent to 5 mod 6, and I want 2 mod 3. So they're consistent in this sense. You do not have this. Just because something is 2 mod 3 doesn't mean it's 5 mod 6. But if something is 5 mod 6, it will be 2 mod 3 because 5 is equal to 3 plus 2. So I see it now. I should pick a p that is congruent to 5 mod 6. I compute a k according to this relationship. 3k is equal to 2p minus 1. I define m is equal to n to the k. Then I will get m cubed is congruent to n mod p. So my strategy is, number 1, I set my p is congruent to 5 mod 6. Number 2, I define k such that 3k is equal to 2p minus 1. And I define m as equal to n to the k. I'm given an n, I found a p, I found the m, done, QED. Okay, so now I'll write the solution. Let p be a prime such that p is congruent to 5 mod 6 and p doesn't divide n. I need the condition that p does not divide n so that I can use these two congruences. So before moving on, I need to show that this p exists. P exists by, there's a fact about prime numbers called Dirichlet's theorem. Theorem says that any arithmetic sequence A0 plus di where I equals 0, 1, 2, 3, etc. has infinitely many if A0 and D are relatively prime. So meaning GCD of A0 and D is equal to 1. In this case, we're looking for 5 mod 6. So the sequence 5 plus 6i has infinitely many primes. So first of all, there are a bunch of primes, so just pick one. And second of all, we needed p not to be a factor of n. Well, n is a finite number, so it only has finitely many factors. So just go past all of them, and then you'll get a prime that is not a factor of n. In fact, just to make it easy, just pick a prime p that's greater than n. If it's greater than n, it's not going to be a factor of n. So I got my part 1. I got my p that is congruent to 5 mod 6. Now I need to calculate k. 3k is equal to 3 minus 1. Right? P, because it comes from this set, that means it'll be equal to 5 plus 6h for some positive integer h. So 2p minus 1 is equal to 10 plus 12h minus 1, and that is equal to 9 plus 12h. And I'm going to define my k as 2p minus 1 over 3. And that will be equal to 3 plus 4h. And I'm going to set m equals to n to the k. So I got the existence of p, I got the existence of m, I got p satisfying the conditions a and b. All I need to do is now prove that part c is satisfied. M cubed is equal to n to the 3k is equal to n to the 2p minus 1, which is equal to n to the p times n to the p minus 1. And all this is congruent to n to the p is congruent to n to the p minus 1 is congruent to 1 mod p. So that's n mod p. There we go, QED. Hope that's been fun. Subscribe for more contents. Thanks for watching. Bye.